Hi, this is Christian, and I'm going to show off my 8 puzzle solution. So to start, I have the breadth first solution. This is the easy puzzle. So I have a whole 8 puzzle builder. This sets the initial state 134, 862, 705. That's the easy puzzle. I have the set algorithm as breadth first. And then I build, and then all the way down here, I do easy puzzle solve. Okay, so I'm using Java in Maven. So let's do Maven package. That builds it, then Java jar, and you execute the jar. And this is the breadth first solution. Start node, all the way down to the goal node, and then the statistics that were gathered during that run. Okay, so let's see how we model the 8 puzzle. We have the initial state as a grid node. We have the goal grid, which is not a node necessarily. We have a frontier data structure. We'll see that in just a bit. And then it optionally has a heuristic if, of course, it's informed. Okay, so the actual searching happens in this solve function. And so what it does, it's what you'd expect. The frontier, it adds the initial state. That's where it starts. And then it loops while the frontier is not empty. And inside the loop, it pops from the frontier. You explore that node. And during the exploration, you find the successors. And for each successor, you add it to the frontier, which could fail if it's repeated state. So it does check that. So I model the solution as an exception, actually. So inside this, it can throw an exception if it finds the solution. So I catch it out here, and what it does, it climbs all the way back to the start node, which has no parent, so it will be null at this point. And I push it down on a solution stack, and then I can pop it off, and then that's your solution. Okay, so here's exploration. It's as simple as add to the already explored list. If the grid equals the goal grid, then you throw the solution. Otherwise, you generate the successors. Let's go into this one. So this is pretty complicated. It essentially checks the grid to see if you can move left, to see if you can move right, to see if you can move up, to see if you can move down. And then if you can, it appends it to a successors list, and then that's what it returns. Okay? So now let's go to the frontier. Frontier is complicated because it hides a lot of the complexity of the algorithms. So if you say you are going to run a breadth first search, it will actually choose the data structure type, which in this case it's a queue. So it makes an array DEC, which can be used as a queue. It can also be used as a stack. So we do that for DFS. But for uniform cost, best first search and A star, we use a priority queue. And the priority queue, it is ranked based off whatever you tell it to be ranked as. And that's our evaluation function. So for uniform cost, it's based off the cost to get there, the G of n. So that's what we do right here. For best first, it's based off the heuristic. So it uses the heuristic to compare. For A star, it's based off the cost to get there and the heuristic. So it uses both to order the priority queue. Okay, and for checking for repeated state, if it's already explored, yes, it's repeated state. If it's in the frontier, however, you check first if it's the frontier is a priority queue. That means that there's an evaluation of the node based on cost. So if it's not a priority queue, it's something like DFS or BFS. So return true if it's in the frontier. You're not going to want to consider it. However, if it is a priority queue, then you want to also compare the node you're trying to add with the node already in the frontier. And if it's a better cost, then you actually remove the one that is already in the frontier because you're going to add this new one. So it's a bit complicated. Otherwise, when you add a node, you see what type of frontier it is. If it's a stack, which is DFS and iterative deepening, then you push onto the stack. Otherwise, if it's a queue, you add. If it's a priority queue, you add again. But of course, we have to downcast. So the frontier is generic. It could be multiple different underlying structures. So it gets a bit messy here where you have to downcast. Okay. So lastly, I'll show off the heuristic I designed, the H3 of n. Yep, it's right here. So it's actually the sum of Manhattan distances. However, it is weighted by the actual tile. Because the Manhattan distance, it assumes that the move cost is 1. So if you actually weight it by the tile, you multiply it by the tile, it's going to give you a better estimate of how far you are from the goal. And that's because this is a modified 8 puzzle.